Now, lecture 2 was supposed to be the heavy one, and now we have 25 minutes to go through it. So what I will try to do is to skip a lot of details and go to some of the concepts, okay? And if while I flip through you see a slide that looks interesting, stop me and we can discuss it.
I might help you tomorrow.
Okay. So, okay. So a few concepts. The first important one is that to verify an ensemble system, so a forecast of a probability distribution function, you have to think, you have to look at a big number of cases. You cannot verify a probabilistic system on one case only. The probabilistic system is going to give you a probability of 20% of snowfall in New York, 80% probability of more than 50 centimeters of snow. Then it snows 10 centimeters. Was this a good forecast or a bad forecast? You cannot say based on one forecast only. Okay, you have to look at a lot of cases. So this is the first concept. These are the topics that I was planning to discuss. I might skip some, as I said. Because the probabilistic system, ensemble system, provides you with a lot of information, there are different ways of looking at its accuracy, and it depends on what you want to do with it. So it also depends on the user application, okay? But so there are a lot of metrics which are used. Brier score, area under, relative operating characteristics, hit and false rates, continuous run probability skill score, ignorance skill score, score and skill score. So depending on the use, one might be more appropriate than another. It's rare that one metric would tell you that the system is good and another that it's bad. But depending on the score, you might, for example, rank systems differently, okay? So the first thing that I said that is essential, and this everybody agrees, is that the ensemble must be reliable. So one way of measuring reliability is how does the ensemble spread on average, dashed, compare to the measure as a standard deviation measure, compared to the error of the ensemble mean. You want the two to be as close as possible, okay? This down here is the difference between the two for the past 4 years in the summer, where you see that there is a very good reliability up to day 7, say, but then there is some under dispersion. This is for geopotential height, 500 over another hemisphere. If you look at winter, again, the last 4 years, much closer, okay? Difference is order 5% at the end. So system is very reliable, more in winter than in summer. Why? Because singular vectors, and we go back to some of the questions you asked me. So singular vectors are computed with a low resolution model, which is good to simulate perturbation growth during winter, where it's more baroclinic instability that drives it, and less moist processes convection. In summer, where the moist processes count more, the linear and adjoint has a poorer simulation of them, the linear approximation is not as valid, and so the system works less well. This is why the two are not exactly the same, okay? So that was one measure of reliability. The other one, the more commonly used, which would bring us to a Brier score, is to look at the probability, the forecast probability versus the observed probability. So as I said at the beginning, you can verify an ensemble system, a probabilistic forecast is only in average terms. And what you want to see is that if I predict an event to occur with a probability of 60% on average, I want to see it happening 60% of the times. So on this reliability diagram, what we try to aim is to have the curves to lie as close as possible to the diagonal. And the Brier score is a measure of how close you are to this diagonal. So what I'm showing here are this probability for some dichotomous events. This is the probability of total precipitation in excess of 1, 5, 10, and 20 millimeters of rain. This is for 2 meter temperature below 4, below 8 degrees, above 4, and above 8 degrees with respect to the mean. And this is 10 meter wind speed. So you want to be as close as possible to the diagonal. This is day 4, forecast verified against observations at synop stations. So what you see is that the system is not terribly reliable, but not too far from the diagonal. Okay? And the Brier score is actually a measure of how close the curve is to the diagonal. I think because you're going to talk about Brier score, I'll skip the definition. Okay, so here you have some examples of sensitivity of a Brier score to the definition. And then let me just show you this. So the Brier score is the Brier score of a forecast versus the Brier score of a climatology. You want to be as close as possible to 1. 0 means that you are as skillful as a climatological forecast. This is for temperature at 850 hectopascal. The event is temperature anomaly above 0. This is how the system looks in summer 14, 13, 12, and 11. What you see is compared to climatology, the system is skillful up to day 15. So it's worth to run it because the information you get out is better than the information you can get out from climatology. So if you remember Anders' Markov chains, by the 6 hour to 6 hour rain to dry prediction, that Markov chain was skillful up to day 2, and then it would give you the same information as climatology. What this tells you is that at day 15 we are around that level. But up to day 15 there is value in using, in this case, temperature at 850 prediction of an anomaly.
Excuse me, Roberto, but that is not due to the fact that you are making an evaluation over the entire North Hemisphere. So that if you reduce the scale, the area, maybe that this 15.
No, because the event is defined in terms of a model climatology and in terms of a standard deviation. So we take that into account. Each grid point, we predict, for each grid point, the climatology is different. And the event also is different. It's defined by the standard deviation at that grid point. In this case, it's 0.
Anyway, you will make an average over the domain.
We make an average, you make an average of a score.
The point was that the Anders before showed the results in 1 point.
Yeah, this is essentially this. Yeah, this is the score of.
You make an average of the Northern Hemisphere after.
I compute the score.
For each point and then you average.
Yes.
And this procedure of averaging does not reduce the.
This is the average score, not the score of the average.
But I don't intend to compete with a Markov chain with a European Center model. So they just qualitatively behave in the same way.
Yeah.
On the other hand, I think, as far as I remember, if you make this verification only for Italy, then it will be quotation mark worse.
Yeah, it will be, I don't know whether.
The smaller, it will be more difficult to get it right, and good.
Yeah, but it's because I mean it's because the verification would be noisier on a smaller region. So by doing it over another hemisphere, we collect more grid points, and so the statistics is more stable. But so it's true. The point when you reach the climatological value might change for different regions, but it's not that. I mean, the score is properly defined. It's not that we see a full score because different regions have different climatologies. Okay. And this is for winter. Sorry, yeah, for winter, which is higher values. The continuous run probability skill score is actually the one that at the end of the day we use more because it's a good score that conveys how the forecast PDF is close to observed PDF. It's the equivalent of a root mean square error, but for probabilistic. For probability distribution function. It measures the distance between an observed PDF that you can make it as a delta function, or you can make it a very narrow Gaussian if you add a small observation error, and your forecast PDF. This is the definition. I mean, in here I simply applied. If you can using Excel code in different distribution. For example, here you have two normals, the forecast B. The observation is another normal which has a much tighter, much smaller error bound around it, and you can compute the continuous run probability score of the two. In this case, for example, the B distribution, which is farther away from the observation, both in terms of a mean and in terms of a spread, has a worse, larger error. And this is how our ensemble looks like. If you consider the continuous run probability skill score, the difference between the continuous run probability skill score and the Brahe score is that the continuous run probability score looks at all events. It's not limited to a particular threshold, while the Brahe score, skill score, is only valid for a specific threshold. Sorry, I need to break a minute. The other metric which is often used is the area under a relative operating characteristic, which is what Anders mentioned a little bit earlier. And why is it useful? Because sometimes you need to take actions. So you have a forecast, a probability that something will happen. For example, here, probability that the observed temperature would be higher than 3.5 degrees. Now you can, and you have to decide whether to take an action that might cost you a certain amount C, or not take any action. If you don't take any action and the event is observed, then you might incur a loss L. But if you protect, you always spend C, whether the event occurs or doesn't occur. While if you don't protect, you might incur a loss L if you take any action. But if you don't, if the event doesn't happen, clearly you don't lose anything. So there is the area under. So you can look at forecast and build a similar contingency table where you compute the probability that the event would occur or not. You can compute the probability that temperature would be above 3.5 degrees. And then by comparing these two, you can define a score which is, well, first of all, by looking simply at this contingency table, you can define the area under relative operating characteristics. And then by using these two combined, you can define this potential economic value of a forecast. Now, I don't want to spend too much details on it, but I just want to show you.
I will show you.
Okay. How a rock area, again for the same variables as we looked at before, for a probabilistic prediction of temperature at 850, anomalies, positive anomalies would look like. Okay, this is rock area is above 0.5, between 0.5 and 1. So you want to be above 0.5, this is 0.6. So what you see, but if you think about what you've seen as in terms of brass core, rock area, continuous run probability score, so they give you a different flavor. You might, if you're a user that needs to take action, prefer to look at this type of measure. But at the end of the day, if your system is skillful, it will have a high value with all measures. If it's not skillful, it will be low, and then maybe it will give you a skillful or valuable information for certain users and not for others. And this is how these curves has been generated, okay, by computing and comparing the economic value of the forecast. The other area that I want to focus a little bit now is the fact that our forecasts don't see all the scales. And so it's bound to give values, especially intense, extreme value, which are much lower than the observed one. So how can you renormalize or calibrate a probabilistic forecast to take that into account? This is extremely important, especially if you want to predict extreme events. High snowfall in Bologna 3 days ago, snowfall in New York, or heat waves, or windstorm. So this is from a paper that we wrote a couple of years ago, where we look at, in this case, for temperature. So this is what the observation looks like at Hanover. Maximum value, minimum value, the range is much larger than what the model can see. The model, we had much more data because we had 50-member forecast for 20 years. For the observed climate, we had about 100 values. This is a specific date in a specific season. So the question that we wanted to address is, how can I use forecast from a model that has this climate, which has a 20-year return value, for example, of about 35 degrees, to predict events which in reality has a 20-year return value of close to 38 degrees. How can I go from the model space to the real space in an objective way? So going from probabilities into something that tells me more about the real world, from probabilities in model space to the real world. This is more or less the idea behind this extreme forecast index. The idea is to compare a model. Here I'm showing you cumulative distribution function. So you take a PDF, a probability distribution function, a normal, any normal distribution. Now you integrate and you can compute the cumulative distribution function that tells you something about what's the probability that I see more than 3 degrees or more than 4 degrees and so on. Okay, so we are in this space. We can compute it at each grid point using our ensemble, because our ensemble will give me 51 points and I can estimate this. It will not be a Gaussian, it will be maybe bimodal distribution, doesn't matter. I can still integrate it and build this CDF. I have a CDF of a model which sees this type of events, and I want to say something about reality. We might see more extreme events. How do I go from one to the other? So the extreme forecast index, what we do is we compare these forecast PDFs with a model climate PDF, and we compute the area under these two curves, and we compute an index of how far is one distribution from the other. This tells us something about how extreme is the forecast of that event. In this case, for example, for maximum wind gusts, this is a probability of wind gusts in excess of 25 meters per second. High for these points in Argentina. And in fact, you see also the distribution very shifted. You see extreme forecast values very high. A high extreme forecast index means something extreme might happen. It might be much more than 25 meters per second, and now we could try to see how we can translate it. But there is a clear indication that there is a match between the extreme forecast index, how the two distributions are one far from the other. 2 meter temperature for this grid point is actually not very extreme. In fact, the extreme forecast index is low, 43% compared to 85%. The distributions are actually not too far from the climatological one.
But Roberto, what you have is a forecast in its relative coarseness compared to reality. You have the model climate, also coarse relative reality. And these are combined. And the extremity comes out fine, but it still doesn't, as far as I understand, catch this subgrid.
Yes.
We show in Hannover, which is out of the reach of both the model climate and the...
What is still missing is how you go from this to that value.
You can apply to quantile.
Quantile to quantile, for example, is one way to do it. Or the other way is simply to use this index. You have a statistics of what's happening at certain stations, Bologna snowfall in February, and you have a high extreme forecast index, something extreme is happening, and how extreme is it? Well, you can compute the return period in model space, and then you look at your data and you see a 20-year return period is equivalent to 50 centimeters, so I predict 10, but actually it should be 50, and I give 50.
By the way, for this snowfall in Bologna, the Wi-Fi was close to 1, 3 or 4 days before.
Yeah, I know.
My point is that you don't make a sort of a recalibration.
Well, we do. In some way, we do it because the extreme forecast index is an adimensional number. It has already taken, it has done the renormalization because I have compared a forecast CDF with a climatological CDF. So this is an adimensional number that now you can use, knowing the observed climatology in Bologna, you as a forecaster should translate it into.
But anyway, if I well understand that you make a sort of comparison between the distances between the actual situation, the climate of the model, and you assume that these differences is the same that in the real world. But can you prove this assumption?
Can I prove that the area in the real world would be the same? No, I cannot prove it. But I think it's, as far as I know, this is, what we do with extreme forecasting is one step more than bias correction, or it is one step more because you also take into account the shape of the forecast and the observed PDFs, which otherwise you wouldn't do, because you would just look at the average here, bias correct, or the average here and the average observed, and simply shift by. This is more, because you look at the whole distribution.
But also the original purpose of the extreme forecast index was an alarm bell.
Yeah.
So for example, when I look at the ECW, I see 20% probability of snowfall in Bologna. I, as a Swede, rubbish, nothing to bother about. Then I look at the EFI, and it comes to red.
Yeah.
Because this is an extreme event for Bologna, not for snowfall.
Yeah.
So it should not be oversold. It just sort of an alarm
Yeah.
that wakes us up, and then we, after having
Yeah.
seen it red, we go back and look at the EPS gram for Bologna. It will find out what is actually going on.
Yeah, exactly. So EFI is a very nice product. I mean, it's really something that, it's a calibrated product. It's an ensemble-based calibrated product that takes into account the shape of its distribution, not just, it doesn't just shift, it renormalizes. I encourage you to use it more and more, because it's a really good one, especially because it's based on an ensemble system which is reliable, especially up to 5, 6, 7 days when we generate this forecast. The question, when, since we are talking about verification, how do I verify the EFI? Well, we can treat the EFI as a probabilistic forecast, for example. So we can build, here I'm just comparing an EFI map centered between day 4.5 and day 5, with an EFI map at 24 hours, which is very close to what was observed. And you can do CRPS between these two, or you can do a brass score, or so this is how you verify the extreme forecast index, by treating it as a probabilistic forecast. And in fact, this is what we do now. This is one of the scores that we generate routinely. And this is how the EFI skill score, which is the score of the EFI forecast compared to climatology, compares for 10-meter wind speed, 2-meter temperature and precipitation, verified against observations over Europe for SYNOP stations. So it's skillful, we keep improving it, it's more skillful for temperature, look at the value, 0.95, close to 1, than for precipitation. Wind speed is somewhere in between. And finally, scores evolution. Well, scores evolution plots like this are useful to keep track of how your system behaves and whether the changes you implement are useful or not. As I said, ensemble has to be verified looking at a lot of cases, so you usually look at the season or at least the monthly averages. And and for the same reason why you cannot really look at single events, also looking at single years or single seasons might not be the best way to look at how the system performs, because there are seasons which are more easy to predict than others. So one should, again, here also in this type of plots, look at the trend over many years. And this is how, for example, the continuous run probability skill score of our 500 geopotential height probabilistic forecast have been evolving from the day we started daily production, the 1st of May 94, to today, to the last, to end of November or end of October. So we have more or less the skill, now the system is the same as the skill at the day 5 is the same as the skill at day 3 about 15 years ago. Same for other scores. This is how the CRPSS for temperature at 50 over Europe looks like. So again, indication of gaining skill. So this is what we were discussing before, Carlo. So Europe, if you look at scores over Europe, they are much noisier. They change. There is much more variability. So extracting a signal is less easy than if you look at over the whole Northern Hemisphere. Right, and I conclude my second lecture. So the first lecture, we look at why we should run ensembles. Then we look at how one can design ensemble. First of all, identify what one should simulate, initial uncertainties, and model uncertainty. Different global systems have been designed in different ways, and the design impact has an impact on the performance. Some designs work better than others. The ensemble accuracy and reliability depends on how good the model is, how good the initial conditions are, and how good are the strategies to simulate model and initial uncertainties. This closes the first lecture, and then we move to the second lecture, which was more of a assessment of the skill of ensemble system. It's more complex than single forecaster. There is a range of measures that we usually use, which are the equivalent of measures we use for single forecaster, but applied to probability distributions. But there is not a big difference between the different measures if you look at in average sense. I mean, if one system is skillful according to one, usually is skillful also according to the other. So there is less opportunity to cheat. If one uses a proper score, continuous run probability score, or Brier score, or rock area gives you the same information. The nice fact of a continuous run probability score is that it integrates through thresholds, while Brier score and rock area you need to pick a certain event. So they apply to a specific dichotomous event. You need to decide your threshold, build the probabilities, and verify that. So once you know that score, it's difficult to think about another threshold. The continuous run probability score gives you a more integrated view. Essential to keep in mind that you cannot verify an ensemble system, probabilistic forecasting system, looking at single events only. You need to build the statistics. Say around 100 cases is good enough, usually, to give you a good impression of how the system is performing. And with this, if you have questions, otherwise if you are